Right. Good. Well, I was going to say good evening. It's evening where I am. Good evening, good afternoon. Hello to wherever you are and whichever time zone. Okay, so this week we're going to start talking about graphs. I think there's a great developer who works at Google, and he posted a list of some of the things that are like the most useful to know as you go to interviews or anywhere in your career as a developer. And he said, I think he said like 50% of the problems he saw posted, like interview problems, you could probably solve with some sort of a graph attack, which is kind of amazing. So we're going to learn one of the best, bang for your buck topics of computer science and applications. I certainly know that I've solved, hacker rank problems, and I sort of brute forced them. And then later I went, oh wait, I could have, if I had known how to think of this as a graph problem, I could have solved it with a graph application. So we're going to learn how to attack problems in this way. I think so as you've already seen, if you reviewed the pre-course videos, there's a fair amount of some graph terminology. So what I want to do tonight is I want to go over like an intro to graphs. We'll go over graph types and their terminology, and we're going to go over two traversals. So our very first graph algorithms. But after the intro, I'm going to be guided by y'all as to what to attack first. So, I want to go through this in whatever way makes most sense to you. First of all, I want to do a graph intro. So let me share my screen. Okay. Right. So let's start off thinking about networks, because more or less a graph is just another word for a network. So what kinds of networks can you all think of? Social networks, yeah. We've got our Twitter, we've got Facebook, we've got LinkedIn, we've got Instagram. What are the kids on these days? TikTok, right? A ton of others. So social networks for sure. Yeah, cellular networks. So here we have a great example of like a physical network, right? You have all these, towers are all wired together. Yeah, GitHub. Electrical grids. Yeah. Yeah. What other, I like these physical examples. What other kind of networks can we think of? They don't have to be physical. Cryptocurrency. Yeah, that's a great example. So you've got a bunch of people who are, as we just did this the other week, right? So we're all working together to mine cryptocurrencies. So that's an example of a software network. We're all part of the network because we're all just, messaging each other's computers. Neural networks. Yeah. Like also, in our brain, or like our actual brains are neural networks, right? And AI networks. Let me see. I think I have that down here. Yeah. Neural networks. How about for like ideas? Anyone ever make like a mind map? Actually, I don't think I have a slide for that in here. I think you've probably seen mind maps before. you scroll down one idea, then a bunch of other ideas and start connecting them. How about, I think down here I have like decisions. If I decide to, I don't know, you could think of it. So here, this is, I found this somewhere on the internet. This is, I think we're deciding like how to call the fire department. And so how this decision flows, if alarm 1 goes off, then we're going to make call 1. And so, we'll go down this path. Otherwise, we might make alarm 2. And so we go down this other path. So decisions, you could also think of those as networks. I even like to think of, I was thinking, could we think about shared interests? Like if I'm friends with someone, what interests do we have in common? Write down all of our interests and start linking to them. Memories. What if we have a mutual friend and I share some memories of that friend and you share some, and we have like some common ones? Flight paths. Those are a great example of a network. Roads and cities. So anyway, all of these are networks, and in computer science, we call them graphs, and that's just a word we stole from mathematics. So when we say graphs, we're coming up with ways to describe all of these networks at once. 6 degrees of Kevin Bacon, yeah, like in real life, social network. Going back to the first one, you can start asking, who does Kevin Bacon know? Who is in Kevin Bacon's extended network? And, conceivably, there are some people that are just not in Kevin Bacon's network. There's like an isolated group of people somewhere. And so no one that Kevin Bacon knows anywhere, knows anybody in that, isolated group of people. But of course, the whole point of Kevin Bacon is he, knows like everybody in Hollywood. So in computer science, we call them graphs. And so when we think about graphs or networks in computer science, we're going to think of ways to talk about this that could be any kind of network, whether it's friends or roads, which is kind of cool. It's cool that we can have this, we get a lot of power when we think this sort of generally. We're gonna come up with these sort of mathy ways to think about, everything from roads to brains. Like at its most, how would you describe a network in general? I guess, what's like the most abstract way you could think of? What makes something a network? What is a network? Love that photo of Kevin Bacon. What makes something a network? Yeah, I think things that have, connections, things with connections to each other, things with relationships. And y'all are already on it. In computer science, we call the things, we call them nodes. The connections we tend to call vertexes or vertices. What things do we, how do I want to put this? What operations do we want to run on our networks? Like think of any example, and whether it's a social network, whether it's a road, what do we want to do on these networks? What kinds of applications do we want to do? Search? Yeah. We might want to pass information from one to the other, communicate. Great. What if we're talking, say, maps, like say this flight path here, or these here? Like search still applies there, right? I want to know if I can get there from here. You know, like if I search for a road from, you know, whatever, you know, the continental United States, from California to London, I'm not going to be able to find that, right? That search is going to come back and say, no, you cannot drive to London. You just can't do it. But it should be able to find a road from whatever, California to Boston. Avoid traffic. Yeah, we might want to find the fastest route. Yeah. Might want to find the fastest route, might want to find the shortest route. We already talked about search. So suppose I want to get introduced to someone. That's also kind of a search, right? I want it because first, you know, I need to find if, oops, you know, so if we're, you know, if we're over like there and we want to be introduced to someone, you know, over here, we need to find if this person over here is in our social network at all. And then we might also want to know the shortest path to get there. You know, I probably don't want to talk to this person to introduce me to this person, to introduce me to this person, and then, you know, wind all the way down here. I'm going to be talking to a lot of people. I would like to be introduced in a pretty, you know, pretty straight line to this person. So I still want to find like the shortest path in that example. Show you a different example. Suppose this is our military network, or suppose it's our enemy's military network, and we're going to send in a targeted strike. If you'll pardon this kind of a violent analogy. We're going to send in a targeted strike. You know, where might we want to strike to try to disrupt their communications? Do we want to try to strike over here? Or maybe I would say we probably want to strike somewhere in the middle. Yeah, everywhere. We probably want to strike somewhere in the middle. And the idea of that is, oops, we have another example here. Here's another, the idea behind that is what we can call strongly connected components. So clearly, you know, if I'm going to try to take down someone's communications, then, you know, severing, you know, this connection here between these two nodes is not going to do it. They're still going to be able to talk. But if I sever this connection, you know, suddenly, you know, this entire group over here can no longer talk with this entire group over here. So the strongly connected components also show us, you know, where the weak points are. Or to give maybe a more, you know, positive example, this could also be our electrical grid. And if we're going to have a power outage, you know, where's the most critical parts to watch? Obviously, you know, one of these, you know, like the C to E connection. Yeah, C to E, C to D, you know, D plus, totally. Or like imagine the graph we're looking at now, this could be a social network. And, you know, so C and D are the only people that, you know, can kind of pass on messages or can bring these groups together. Yeah, E to H, totally. That final node coming out of E here, you know, this person is really well connected. Like they know this person here, they know 3 people. They know this person. Actually, the connection's going the other way, but I'll ignore that for now. They know these 2, they know the one over here. But even more important than how many they know is where they are. This person is the only link between these groups. So that's like a node we don't want to take out. Yeah. Cool. Okay. So whenever we think about graphs, if you ever, as we're going through, we're going to build our knowledge of these algorithms. We're going to have all this terminology, but just come back to what it really is. Graphs, with all the terminology that we're going to introduce, are just networks. And at the end of the day, we're talking about, if you translate these algorithms or examples into like, social network or electricity grids or whatever, I personally, I always find that helps me make more sense of it. Now, I'm going to talk about one more thing, and then we're going to decide like where to go, whether we want to talk about terminology and types of networks, or whether we want to start in talking about traversals. So the reason I was asking for examples of things that, examples of, things we might want to do with graphs, with networks, like finding someone, like sending a message out, and so on. If you think about it, most of these examples kind of involve the same couple of operations. Like, let me go back up to my first one right here. If we say, hey, Kevin Bacon, can you introduce us to someone? Like I said, first off, we might want to know, is this person in our network at all? Can you get there from here? Or is the person, sitting over here and they actually don't know anyone? And so as a result, we cannot get introduced to them. This person has no connections. Or if they do have a connection, well, now all of a sudden we can get introduced to them. So that comes down to search. If I ask, can you introduce me to someone? That's really search. If I say, can you send this message to everyone you know, right? So now we want to visit every single person. So I'm like, okay, starting from, say, this person, can you send the message to everyone we know? Like a chain letter, right? She's going to send this to these people, and the message is going to say, hey, email this to everyone you know. And then they're going to do the same thing. And so this, then it spreads out. Right. Like, say, if you're running a marketing campaign or whatever, a political campaign, you're trying to get the word out. So you say, hey, I'm going to send this to everyone I know, and everyone I know, please send it to everyone you know. So very soon, obviously, you're then going to touch everyone in the network. I'm drawing like a random path here, but we're going to touch absolutely everyone. That's called a traversal, where we go through and we're going to touch everyone. Really, search, if I want to know if I can find a specific person over here, we're going to find out that is built on top of traversal. Because starting from over here, we don't know how to find this person over here. We don't know what the path is. So we're going to have to search through all of our connections, searching in one way or another. We're going to have to search all of these people until we find the path to these folks over here. Yeah, spam. Great. Spam's a good example. So our goal might be, let's talk to everyone, contact everyone. Our goal might be, let's find a node. It might be, let's find the shortest path. We might want to find the weakest point. But pretty much, in all these different examples of networks, what we're going to want to do is usually involves traveling across our network. So we're going to start at one node, and then we're going to see if we can get elsewhere. We're going to visit one particular node, or we're going to visit all the nodes. And that's what we call traversal and search. Traversal just means to cross something, like I'm traversing a bridge, if you're not like super familiar with that word. Okay. So that is my quick intro for that I hope will give you some sanity as we go through this. So I'm going to let y'all decide now. Do we want to talk about traversals, like the actual algorithms, or do you want to go through and start talking about, like, say, graph representations? So let me drop a poly in. I will. Make this anonymous. And a second. There we go. Holly did not like my options, the way I was doing it. Okay. All right. I'm seeing a preference for representations. So let's do that. Right, let's talk about graph representations. So the intro to graphs. Learn how to represent a graph as an adjacency list, learn how to represent a graph as an adjacency matrix, and their trade-offs. Right. Okay, so we, as humans, we have this sort of intuitive picture of what a network looks like. It's like dots connected. And that's very easy for us to visualize. And we can, I think, pretty easily imagine, one friend like connecting to another, or, getting two people getting connected, whatever. We can imagine like a message getting passed along. But we need a way to represent this picture in code in some way. So we need to translate our basic intuition of a network into code. And the two most common ways that we do that are an adjacency matrix and an adjacency list. So for instance, here's our example of a graph. And we haven't really gone over the terminology yet. And yes, we are eventually going to discuss all these topics. I still see people discussing the poll. So we haven't learned this terminology yet, but this particular graph that we're looking at is a directed graph. And what that means is that the links have directions. So if this were roads, these would be one-way roads. You can get from A to B, but you cannot get from B to A. And the way we can represent this in, yeah, directed graph. The way we can represent this in Python is pretty simple. We will make a set or a dictionary, a hash map, and every node we're gonna add to our dictionary. And every node will then have a, so every node has an ID, A, B, C, D, whatever, and its value is going to be a set. So a set, if you're not familiar with the set data structure, it acts very, very similarly to a dictionary. It has constant time insertion. So just like adding to a dictionary or hash map or object, you can add things in constant time. And that means you can also check for membership in constant time. I can say, is this in my set? The only difference between a set and a dictionary is a set will not allow you to add duplicates. And a set does not have key value pairs, right? It just has C and D in there by themselves, rather than, B is key and a value of, the set. So a set kind of acts like a list because you can add stuff, anything to it, but its complexity acts like a dictionary, and as I say, it guarantees uniqueness. So you cannot have two C's in here; you can have two D's in here. So we have our keys. Our key is the ID of the node, and its value is a set. So A is connected to B. B has arrows going to C and D, and so we have C and D in the set here. C has a connection to E. Skipping over D, we can see it's E also has a connection to C, and so we have that down here. Coming back down to D, D is then connected to F and G. We see that. So we've added their connections here. And G is connected to A and to F. That is the adjacency list representation. So the great thing here is one of the nice things about this, and we'll come back to this, is it's very easy. It's just easy to work with, I think, in general. If I want to say, who are A's neighbors, who are A's connections, I can just go get the value A and then see what is in that set. A is connected to B. Done. Or I can just access the B key and see what are B's connections. You're connected to C and D. In an adjacency matrix, this is kind of fun. So we're going to represent this graph as they say, as a list of lists, where each row here is going to represent one node. So right here we have A, and we have a 0 if it's connected, if this node is not connected to that node, and a 1 if it is. So this is A. It's not connected to itself, but it is connected to B. A is connected to B, right? We can scroll up here and see that it's connected to B, and so we have a 1 there. And here we have the B node. So B is not connected, does not have a connection, does not have an edge. We also call a vertex an edge. We call it a connection, we call it an edge, we call it a vertex. Those all mean the same thing. So B does not have a connection to A. B does not have a connection to B. But we do have a connection to C and D, as we can scroll up and see. And so we have 1s in those places, and then 0s in all the rest. Coming down to C, again, so we have, what is it, A. Let me scribble in here a little bit. So we're A. So here we have, so we're looking at C right here. So we have A, B, C, D. We do have 1 connection to E. Wait, did I do that right? A, B, C, D, E, yeah, F, G. Yeah, and looking up at our previous representation there, we can see the same thing. C is connected to E. Right. So that is an adjacency matrix. Yeah, good question. Can the adjacency list only be used with directed graphs or undirected also? You can use it with undirected graphs. So come back up to our adjacency list. So if all of these were, if this were undirected, then we would say if A is connected to B, then that means B is also connected to A. So we would have to be sure to do that. So if I'm, oops, I did not mean to do that. That's fine. Suppose that I'm like adding a connection, like suppose A was not connected to anything. Suppose I start with 2 nodes here, right? And I'm gonna add a bunch of other nodes right here, and I'm gonna add a connection. I can add a connection here, so there's a directed connection. Now, if this is going to be an undirected graph, so that means that we're dealing with like a network like Facebook. If I'm friends with you, you're friends with me. There are no one-way roads. That's what we mean when we say an undirected graph. It's the same thing as having 2 connections like that. That's the same thing as having no directions at all. So having 2 is the same as just having, a connection with no arrows like that. So if I'm adding a connection from A to B, then I have to go be sure to add a connection from B to A, and then I'm good. Yeah, great question. Now, some matrices, if I think you can, oops, let me go back to my slides. If we think about roads, right? Roads, they connect cities, and also they have distances. We can represent the distance. If I go back over here, suppose I make a new little graph again. So here we have cities, and we have a connection between them. Say it's undirected because it's a 2-way road. But I say this has a weight of 10. This road has a distance of 10. So I say there's a weight there to represent how long it takes to get from one city to the other. And this one might be only 5. These weights are easier to represent with an adjacency matrix. We can see why if we scroll back down. Instead of just having a 1 there, we could have a different number to represent the length of this road. So an adjacency matrix is, as they say here, with this implementation, we get the benefit of built-in edge weights. That's what they mean. We could, instead of just having a 0 or a 1, we can have a 0 if there's no connection. And then when we have a connection, hey, let's put 10 for how long that road is, or the weight. Again, I'm using an example of a road because that's a really natural way to think about it. But it could be, how much it's going to cost to stock our storeroom, depending on what we buy. You could use various things for the weights. Yeah, the nested arrays, adjacency. This is, by the way, this is how we represent a matrix in general. Usually, it's usually a list of lists because it makes it easy to do rows and columns like this. And if you use Python libraries like NumPy or Pandas, they'll print out matrices like this beautifully. They're really nice to work with, matrices. Okay, So those are our two basic representations. Yeah, 2D array. And both of them have their own strengths and weaknesses. So when we're counting, when we're thinking about networks, we have to think about how many nodes we have. So how many, people are we keeping track of? How many cities are we keeping track of? And then we also have to think about connections between them. How many connections have we got? Oops. For instance, actually, let me go touch base on that topic a little bit more. For instance, here with the airports, we have like, a decent number of connections between airports. Most of these airports look pretty well connected to each other. And so here, suppose your job was to fly every route on this, that's going to take a long time, right? Now, all of a sudden, the number of routes that we have, the number of connections we have are more important really than the number of nodes that we've got. If there are not many connections, there's only a couple connections. I'm trying to think of where's a good example of that. Really just the one we've been looking at. We have not that many connections. So really the number of nodes we have might be more important than the number of connections that we've got, than the number of edges. So we might call this a sparsely connected graph. And the one with lots of connections we'd call densely connected. But we only, we only care if it's sparse or dense, if it makes a difference, like if I told you your job was to go fly every route here. Now you care there are a lot of, this is a densely connected graph. You care there are a lot of connections. Okay. So total number of vertices in the graph, total number of edges, average number of edges per vertex. So the space complexity. I just realized I've been saying vertex incorrectly. Vertex is synonym for node, not edge. Right. So the space complexity is on the order of OV squared, and we can scroll up and see why that is. Right. Just to represent this, even if there are no connections, we still have to have a space for it. So like there's certainly not going to be a connection from A to itself right here. This is the A row, and A is never going to have a connection to itself, but we still have to have a 0 there. And the same for all the others. Obviously B is not going to have a connection to itself, but we still have to have a 0 for it there. So we have the number of, we have the number of nodes. We have as many rows as we have nodes or vertices, and we have as many columns. So it's V squared. Both of those equal the number of nodes. I'm going to stop trying to draw here. That's really. Whereas with an adjacency list, we have on the order of vertexes plus number of edges. So scrolling back up to here, you have to have a key. You have to have one key for every node, for every vertex you've got. And then how long are these lists going to be? Well, the lists are going to have as many members as you've got edges, right? So B has two connections, 2 edges. So we've got 2 in B's set. So consider a sparse graph with 100 vertices and only 1 edge. We have 100 nodes, we have 1 connection. So an adjacency list, we have 100 nodes and there's only 1 connection. An adjacency list is going to have all 100 nodes as keys, but then it's only going to have one of its, there's going to be 1 set with something in it, Like, so A has a connection to B and that's it. So A is going to have B in its set, and all the other sets will be empty. So that does not take up too much space. Yeah, so Wilfred, the adjacency list will, let me ask you your question here. So you're asking, will the adjacency list have a fixed amount of memory regardless of whether it's a directed or undirected graph? I think that's almost true. Just remember, if it's an undirected graph, then we have to add more connections. So if this was an undirected graph, if A is connected to B, then B is connected to A. So we would need to come down to B here and add A in there, and that's going to take more space. So if it's an undirected, then we're going to need to take up more space. Right. So coming back to the explanation here, if we have 100 nodes with only one edge, an adjacency list is going to be much more efficient because the adjacency matrix, we have to have this entire matrix, even if there are no connections. It's still going to have the same, it's still going to have, 100 times 100, spaces in this matrix. We have to have 100 rows, we have to have 100 columns. Yes, yeah, that's right. That's right, Wilfred. So the adjacency matrix will have a fixed amount of memory, regardless if it's a directed or undirected graph. Regardless if there are any connections, the adjacency matrix is going to need all these rows and columns in the matrix. On the other hand, if we have lots and lots of connections, then, so every node is connected to every other edge, then the total number of edges will approach V squared. So now we're taking up basically the same amount of space. Doesn't matter which representation you use. But as they point out, an adjacency matrix is just using lists, and a list is a very simple data structure. It's an array. It's very simple to implement and does not take up a lot of space. So if we have a very densely connected graph, the adjacency matrix actually becomes more efficient. For adding a vertex, let's see how hard that is. Adding a vertex is extremely simple in an adjacency list. You add a key to your dictionary and you set the value to be a set, an empty set. So I'm adding A. So now I add this node, I add A, and I set the value of this node to be an empty set because we have not yet connected this to anything else. And adding a new key is a constant time operation. Pretty easy. On the other hand, suppose that we have an adjacency matrix. And maybe we already even have, we already have these vertices here. That means that we have these lists, right? We have that row for A, we have this row for B, we have another row for C. Now, if we want to go and add node D, we have to add a new row there. Okay, that's pretty easy. But then we also have to come and add a 0 to each and every one of these down here. So we have to add a new value to the end of each row and then add a new row at the end. So we have to iterate over all the edges, append a 0 to the end of each of them, and then go ahead and append, this whole thing here is going to make an array of zeros of the proper length, and then we have to append that to the end. And usually it's O of 1, but if we have to resize the array like we found the other week, then that's going to take up more space. So adding a vertex to an existing matrix, very efficient in adjacency lists, but inefficient for adjacency matrices. Now, removing a vertex, not so great in both ways, and kind of for the same reason. We have to go through and remove all of the connections to that vertex. If I scroll back up, if I remove, B, then we also have to remove A's connection to B. So if I'm going to delete B right here, then I also need to go through, I don't know what other nodes are connected to B. So I need to iterate through and find B and delete that. And the same down here. I can delete this row, but now I need to go find who else has a connection to B, and I need to delete this space here. So I don't need to find who has a connection to B. I just need to delete that space regardless. So that's not going to be very efficient. Yes, we get to see the matrix here. Where was I? That was remove an edge. No, I'm sorry, that was remove a vertex. Right. So as they say here in adjacency matrix, we have to remove the removed vertex's row, which is easy, but then we have to go remove the column from each other row. So as we learned the other day in arrays, we have to move everything over in that element by one slot. And the same for an adjacency list. We need to visit each vertex and find and remove all edges. So it's still, removing from the sets and dictionaries, we have a lookup and then we have a removal. Both of those are O1. We have to iterate through every one of them. So we have to go through every one of them. So that's linear, an adjacency matrix. We have quadratic time complexity. Adding an edge in an adjacency matrix is quite simple. So here we already have all the nodes. We're just going to add a connection. We say, okay, you two, you're now connected. You are now friends. So if this is a directed graph, we're just going to go to the right spot and change that 0 to a 1. If I scroll up, if we want, we want A, that's our 0th node. So we'll access that. And then again, we use our access to say, go here and change that to a 1. And then congratulations, A has a direct connection to C. That's adding an edge. Adding an edge in an adjacency list, also simple. We're going to go look up the key in the dictionary. Its value is going to be a set. And so we call .add on the set to add a vertex to our set. Both are constant time. So adding edge is very efficient. Removing an edge. So you two no longer know each other. Let me scroll back up. Ronnie, in this case, if you're asking, which one are you asking about? Are you asking about removing an edge? Yeah, for removing an edge. Yeah, so you see here, if you're asking about, I'm not sure exactly what you're asking about. If you can clarify. Yeah, so in the matrix, so yeah, are you talking about, yeah, Ronnie, you sound like both are good questions. So if we're removing, yeah, so, okay, you're probably asking about removing a vertex. Removing a vertex. So I remove B, that's right, in that example. In that example, we actually have to remove the 0, which remove the column altogether. Let me scroll back up and say that again. So we're talking about removing a vertex, so we're going to kill the node altogether. So if I scroll up, so in this example, we're going to say, I want to just chop this out. B, you are no longer in our matrix at all. To accomplish that, in a list, we simply remove the key. So we're going to delete this out altogether. And then we have to iterate through and look at all the other sets. And here we find an example, so we remove that. The others don't have the other sets, so we're going to look at them to be sure. We're going to go down and look at them. But they don't have an example of B, so we don't have to do anything. In adjacency matrix, to delete B, we would need to remove this row altogether. That goes away. And now all the other rows have an extra column. They have this column. We have to remove this column. This is the B column, and it has to get deleted altogether. So that has to get removed. So we have to absolutely, delete this. B is getting removed from our universe. So it's not quite as fast as Thanos snapping his fingers, but yeah, very expensive operation because we have to shift everything over essentially. Yeah. So we're not just So that's removing the vertex, removing the node. We have to go and delete everything. Now, when can we just change it to a 0? When we're removing an edge. We're saying, you two, you're still in our matrix. Both of you are still in the matrix. We have A, we have B. You're still in the matrix. But you used to be friends, and now you're not. That goes away. So to remove it from an adjacency matrix, now we just change that 1 to a 0. Pretty easy. And so we come up here and we would change that, the 1. And so in the first row, we have a 1 from A to B. We just change that to a 0. Pretty easy. To say that A and B here are no longer friends, we would just delete B from A's set. So this gets deleted, but the B stays in. We're not deleting this, that stays there. So now A and B are no longer friends. Right, so both are constant time operations. No, wait, I'm sorry. That was add edge, but that is also the case for remove edge. And now we want to see if two nodes have a connection. Are you two friends? Is there an edge between these two nodes, between these two vertices? So we just look to see in adjacency matrix, we look to see if that value is not 0, it's greater than 0. And in Python, we can just say, this is the syntax for looking up if a value is in a set. So we ask, are you in my set? So if V1 has a connection to V2, then V2 will be in the set for V1. Now we want to get all edges from a particular vertex. So what this means is we want to get the neighbors, we want to get the friends for a particular vertex. So I say, get me everyone that this vertex has a connection to. Give me everyone this node is connected to. And so with adjacency list, we just say, yeah, no issues. Give me the set, easy. And adjacency matrix, a little more complicated. So as you can see, we're going to say for V2 and self.edges V. If there's a 1 there, then we'll say, then we append V edges, we append that to our edges. So we have to, let me go up and show that here. Right. So let's look at, say, B, the second row here, 1th row. we only want we don't want the people B is not connected to. We want the people B is connected to. So clearly, that's just those two. So we're going to iterate through. And so we go for every value here, dot, dot. If it's a 1, okay, then we're going to, then we're going to append that. So we have to iterate through and check which of these values are 1s. So because we have to iterate through for adjacency matrix, getting all the edges, getting all our neighbors is linear time. And that, I think, about wraps up there's our once around the world for our matrix representations. Further questions on that? Something you want me to go over again? Which of these do you like better so far? Which of these do you like better? Which would you rather work with? If I ask you to code up a matrix, code up a graph, which would you rather do? Adjacency list, matrix? Seeing a lot of lists here. Matrix, love for Keanu Reeves. That's fair. Everyone loves Keanu. I think adjacency list is usually easier to work with just in terms of the code. Yeah, and Wilford's got it. It's always going to be situation dependent as to which one is easier to which one's easier to work with. As a rule of thumb, in general, if you find yourself working like really hard to do your algorithm, sometimes you want to stop and consider if you're using the best data structure. Like even if you might go like, oh, I should be using a dictionary, not a list here. I think there's, who is it? Alan Perlis was a computer scientist. He had these pearls of programming. I think I'm getting the right guy for that. And he said something like that. Data structures are more important than algorithms. So yeah, if you're working really hard, you might want to consider a different data structure. So most of the time, the adjacency list is going to be easier to work with. Sometimes, as Arpita says, matrix is very explicit. That might be easier. Why do we put the value in a set and an adjacency list? Yeah, matrix is a nice visual representation. You can really see how it's laid out. Yeah, basically to reduce duplicates. We don't want 2 B's in here. And so remember, a set is like a list because we don't have key value pairs. We just have, things in a list, in a row. But a set is like a dictionary because you can check if something's in it in constant time. I can ask if C is in this set in constant time. I can put C in the set or remove C from the set in constant time. So sets are kind of cool. No duplicates, put stuff in them like lists, constant time, access like dictionaries or objects. For what could be alternatives of set? You could use, let's think about it. If we used a list or an array, you could do that. You would want to code and make sure that you were not inserting something twice, so we don't wind up with 2 B's or something, 2 C's, 2 D's in someone's list of friends. So if this is a list, we might want to double check that we don't have 2 C's or 2 D's. And the other thing is, if I want to get all of these friends, well, that's also pretty good. I can just grab this list, and that gives me all of B's friends. That's pretty easy. But if I want to know if C is a friend of B's, now I have to iterate across this list. It's not going to be constant time. I have to iterate through it. So it'd be a little slower. You have addictive arrays, maybe. Yeah, there's other ways to do this. We could do, you could do, and actually, what if this was weighted? So I want to know how long it takes me to get from B to C. Maybe then I want to say, C has a weight of 5, right? So now I want to use not a set, but a dictionary. The distance from B to D is like 3, right? So it would depend how we want to do what we're using this for. Yeah, extra logic to disallow duplicates, totally. But for our application here so we have so this graph does not have distances, aka does not have weights. So there's no distance from A to B. It's just a connection, like Facebook. I'm friends. I don't have a distance on Facebook. So there's no weights. Then this works real well. Yeah, set is an elegant data structure for a more civilized age. All right, let's take a 10-minute break. When we come back, we will do, we can go over some terminology real quick, but I want to dive into traversals and give us enough time to go through that. So let's take 10 minutes. All right, and we are back. Right. Let's do, first of all, let's code up our adjacency list. And then we will go and look at our traversal algorithms. So actually, let me go back and share. Yeah, I'll share that entire desktop. Right. So if we go into the project here, go into our project, we go into graph. We have our first day's work. So we're going to, what we're going to do right now is we'll implement or look at our graph class, and then we'll go back and look at the ideas behind traversals, and then we will start implementing that. So let's do this here though. So if you, in this file, if you click on graph.py, you see what I've got my code editor on the left. Yes, thanks for posting that, Edgar. So let's do the first few methods here. So if you open the graph.py file, you'll see, from util import stack and queue. We'll come back to that after we do our traversals. So when we instantiate our graph class, it will do self.vertices and empty dictionary. So when we are adding a vertex to the graph, how should we do that? So we're going to call, so we'll do something like, graph equals graph, we'll instantiate our class, whatever that is, and then we're going to call add vertex, and it could be, maybe like A, right? Oops. What should the add vertex method look like? We're going to add a vertex to the graph. We know we have our graph is going to be an adjacency list, the adjacency list representation. And in an adjacency list, an adjacency list, we want the keys to be the vertex ID, and we want the value to be an empty set, because so far, this node, this vertex, has not got any connections. So it's an empty set like this. Then, okay. So now let's suppose we've added a couple of vertices. So that means that we've got, A is an empty set and B is an empty set. How can we add a directed edge to the graph? So we want to connect them. We're going to say, A, you're connected to B. For instance, this could be Twitter. If I follow you, then I read everything you write, but you don't follow me, so you don't read everything I write. So how can we add a connection? We want to say, B, A, you have a connection to B. So B, you're in a set. So it's a one-way. Repeated points out, check first if they're in the self.vertices. Right. So something like if the one in self.vertices. So we're going to make sure that we have the A. So I'm not trying to add, I'm not trying to access a key that's not there. And if it is, self.vertices v1, now we've got the set. Dot add v2. So that will then, so first we check that the A is in our dictionary. And then we access the value with self.vertices brackets v1. And that gives us the value of the set. And sets, we add stuff to it with dot add. And so we call that. And so that would add like that. And Brett brings up a very good point. Should we do the same for v2? Should we turn this around and go like this? And yeah, if every, let me think how I put this. Also a good question. Also a good point there, Brett. Right. Yes. I thought Brett was asking, should we always add a connection, like that? But that would make an undirected graph, as Arpita points out. Like in Facebook, if I have a connection to you, then you always have a connection to me. But actually, Brett is pointing out that we don't want to say that V1 is connected to V2 if V2 is not in our self.vertices. So maybe we want to do and V2 in self.vertices. I think I can't do V1 and V2 in Python as much as I would like to. I believe I've done that before, Ronnie, and it did not work out well for me. So yeah, I think I can do this though. So this is how in Python we check if the key is in the dictionary. If key in dictionary is the syntax. Python is like hilariously simple sometimes. And if I want to get the neighbors, so I want to say, show me everyone. Can I do that, Arpita? If V1, comma V2 in? I'm going to take your, I have not looked that up. I'm pretty sure I can do the way I'm doing it. And Arpita is suggesting I can do that. But it doesn't like that either. I think I have to do it this very explicit way, sadly. Okay, so get neighbors, get neighbors. Get all neighbors, aka edges of a vertex. So show me everyone that this vertex, this node, is connected to. Show me all your friends. How would I do that? Show me all your friends. So I say, show me all the people A is friends with. What should I do? If this were an adjacency matrix, we would have to, then we'd have to iterate through. If I go back over here, actually I'll go back here. If this were an adjacency matrix to show all the friends of A, I would have to go through here. I have to say, is this the one? Nope. Is this the one? Yes. Or really, is it greater than 0? All the rest are zeros, so no more friends there. So A has one connection to B. Yeah. In an adjacency list, we can very simply return the set. The set stores all the connections. So A has a connection to B in this example that we're building here. So we can, so self.vertices vertex ID gets us the set. It gets us the set that corresponds, for this vertex ID. And so we can just return that set.
So first we will be getting set B here in returning as the neighbor.
So so we can do it in one step. Is that what you're saying?
Yeah, so I'm just guessing the return of this self dot vertices vertex ID. Shouldn't it be returning B for us?
So suppose I call this one, look at give a concrete example, self.get neighbors. Then this is going to do, it's going to return, so it's going to do self vertices A. Of course, that will turn out to be the set with B in it, right?
Yeah, that's what.
And so if I return self dot, you know, if I can type self dot vertices A, then I'm really just returning the set with B in it. Does that make sense? So I can do it in one step that way.
So if we have like multiple neighbors at the same level, will it return me all the neighbors at the same time, or I have to call it again and again?
No, good question. So suppose we've added more. We have C, D, and so all of these are now in our vertices here. I'm just going to go ahead and this is kind of. I'm going to kind of do this manually, but I think that's not a bad thing. Right? So we have all those. And then we call add edge. So we have graph.add edge, and we say A, you have an edge to B. And then we do it again, and we say you also have an edge to C. And we say you also have an edge to D. So now we have C, D. And so to directly answer your question, now when we call graph.getNeighbors here, we will get back the entire set with B, C, and D. That's what we'll get back. We'll get back what's on line 17. Because if I
So we have to call this add edge function previous to adding like getting the neighbors, right? Add edge function should work prior to function get neighbors so that we can get all the neighbors who are at the same level.
Yeah. Now, if I call graph.getNeighbors for C, what will I get back? I'll just get back an empty set.
Empty it's,
Yeah. Yeah. I'll get back nothing. I'll get back an empty set. So, yeah. Yeah. So when we add an edge, we're adding, you know, each neighbor to the set. So when I call get the neighbors, I get all of them at once. Yeah. Good questions. Okay. Well, great job with questions, y'all. Please keep asking. This is really good. So that's a basic adjacency list, you know, representation coded up. That's all we needed. You know, we have we start off with, I mean, I've added stuff here for illustration purposes. Start off with an empty dictionary. And then to add a node, we add the vertex ID, set an empty set, add an edge, check that we can do it, and then just add to that set. To get the neighbors, return the entire set, because that will hold all of the neighbors for that node, for that vertex. And now we have successfully represented our graph in code, which is pretty cool. Okay, I was also going to go over terminology, but I've mentioned all of the relevant terminology as we were going through this. So I'm not going to review it again here. I can review it again, tomorrow night, whenever. So let's start thinking about traversals. So like I said, when we're thinking, that's really great. I'm glad you find it logical. When we're thinking about if you want to be introduced to someone, then you need to, see if they're in your graph, right? You need to see if they're in your network. So you have to search for them. If you want to know what's the shortest road, first you have to, find a route between the places. If you want to send a message to everyone, in all of these examples, the first job is to visit all the other nodes so you can find out what's there. So our first job, the most fundamental task that we've got is to traverse our graph. Your mission, should you decide to accept it, is to visit every other node. You're going to start with one node and you're going to visit all the other nodes. That's a traversal. So I'm coming over here. You're going to start, with one of these, and you're going to go, and your job is to visit every single other node that you can. If you can get there from here, go there. Touch that person, tap them on the shoulder, send them a message. And once we can do that, then we're also going to be able to do search. We're going to be able to do all the other things. So we have to do this first. And this is a traversal, yes. Now, there's two basic ways to traverse. I say there's two good ways to traverse. We could sort of wander around, if I say, if I ask you to start at one spot and go to the other, you could sort of wander around randomly and retrace your steps and, oh no, wait, I've already been here. This is the way we do it when we're in a maze and we don't know where we're going. Obviously, that is not very efficient. We would like an efficient way of doing this. So we have two efficient ways of doing this. Let's look at them. These are breadth first and depth first. Let me open up a empty spot here. Okay. And the great thing about this, let me check Slack. Yes, we have to keep track of what we've already visited. If we keep track of what we've already visited, then we won't be retracing our steps essentially. So the two basic ways they're actually very, very simple, very, very, very related to each other. So even though we're going to cover two here in quick short order, you'll see it's really the same thing. So suppose that we're starting with A. We go to A and we say, okay, A, I want you to give me your neighbors. Give me everyone you're connected to. So we start with A and we say, A, give me your neighbors. And so let's do depth first. This is going to be depth first traversal. So we get A's neighbors, which is just B, right? And we'll put B into a stack. And this is what I'm going to make for a stack here. The B, you go into the stack. And then we so we mark A as visited. So here's going to be people, to visit. And here is going to be visited. So A, you've been visited. We put you there. And we say B, give me your neighbors. And B's neighbors here are clearly C and D. So yes, this is a stack. This is going to be a stack. To visit, oops, I'm going to call this to visit stack. This is the stack. And so B's neighbors are C and D. And we're going to put them onto our stack. So D, so let me be clear here. We put we put B on the stack. Now we're going to say, now we're working with B. You're the one we're working with right now. Current node, you're B. And so D, you go on the stack. C, you go on the stack. And now we're done with B. So B, you go and visit it. You're done. And then we're going to take the first friend. So I said, B, give me your friends. Okay, here's our friends. Give me the first friend. And the first friend is the one on top of the stack. And so now you're off the stack and we're visiting you. C, give me your friends. So we get all of C's friends and we're going to visit C's first friend. And that's E. But let me adjust this here. Imagine that C also has a connection to F. Okay, I want to modify that there. So F, hang on, I put this in the wrong spot there. Sorry. Right. So I get C's friends. C's friends are E and F. So F's going to go on. E, you're going to go on like that. And I say, okay, we're done with C. C, you go there. Now give me your first friend. You gave me your friends, so I know who to visit next. Now give me your first friend. Your first friend is E. So the point here, I want you to notice something. Notice where we went here. Okay, we did A, then we did B, and we did C. Now we're on E. We went down deep. Like B's friend D is not getting visited. D is buried. We keep visiting the first friend. We said C, and so C was the first friend, so we went there. And then we said E was the first friend, so we went there. All right, so we keep visiting the first friend. And as a result, we're going down deep. We're going depth first traversal. So we still haven't, we're visiting all of B's stack of friends before we're visiting the next friend, before we're visiting D. All the other friends, so D is getting buried in the stack. You notice that. We keep putting other people on top and then visiting them first. Eventually we're going to visit D, but not yet.
So a question here. Mm-hmm. So here, instead of like A, B, C, E, means C and D are at the parallel level.
I'm sorry?
C and D are at the parallel level.
Yes.
After they are both of them are friends of B, but instead of going to C and D parallelly, we are going in depth either of D, A, B, D, G, or we are going A, B, C, E, right? In depth first?
Yes, in depth first we're going here. Even though, as you pointed out, if you look from the perspective of B, C and D are at the same level.
Yeah.
But we're not going to.
So depth first,
yeah.
So if I could write it like A, B, D, G also, it's a depth first traversal?
Yes, very good. You could do that too. If you happened to, visit them in that order. This would also be a valid depth first traversal. You could go A, B, D, G. And again, this is going depth. So and then we would visit probably F. And then we would finally come over to B's other friend, C. This would also be depth first traversal, right? So it's that order. So that would also be depth first. So the point with depth first traversal, we're going to do all of this, and then we'll probably, and if there was I drew a connection to F, remember, I drew a connection here. So then we'll probably go visit F. And then finally we come back to B's other friend. So now we're finally doing the other one. So let me keep on with that. So that's a very good point, Arpita. You can do depth first traversal in multiple orders. Where was I? So we went to E, and E has a connection to C, but we've already visited C, so we're not going to go back again. So we're done with E, and then we would pop off. We would go to F. And, again, F has a connection to C. We've already visited that, so we're done. And then finally, we're ready to go to D. So we're ready to go to D. Now we're finally visiting B's other friend. We went all the way down one trail. We're coming back. Yeah. So D, we say D, give me your friends. Call get neighbors for D. And so maybe it calls, you know, let's see, we already, oh, I'm sorry. What did I say? Did I say we visited F? I did say that. So F should be here. I haven't added them in the correct order. E, anyway, the point is we've already visited them. So D, you know, we can put F and G here. Then we're done with D. But we've already visited F, so we're not going to do anything more with that. And then we go to G. We call G's get neighbors. You know, we can see G has connections to A and F, but then we will check and see we've already visited them. We're not going to go visit them again. We only touch them once, and we're done. That's depth first traversal. So because we keep adding, you know, the point is with the stack, we keep adding new friends, and so we bury poor D before we come back to it. That's depth first traversal. So to give you one other visualization, if I come down to here, and let me try to clear these little drawings here. With depth first, you know, you might start here, and then you would look at all of these. You would look at all the green. You'd say, give me your neighbors. Oh, that's all of these. But then you would choose the first friend, and you'd say, give me your neighbors. And then you would choose their first friend. And so you actually visit this one. And then you're finally ready to move on to the next neighbor. And so you visit this one. And then you're ready to move on to the next. So you visit that one. So that would be how depth first would do it. You go all the way down to the end of one branch of your graph. You know, it's kind of like a tree. And before you go on to, so I go all the way down here before I go on to visit this one. Yes, so yeah, using depth first traversal in the real world. And actually I can come back to that. I'll give you a couple quick ones. Going through a maze is a great example. If you know that what you're looking for is going to be at the end, like I'm looking for, I don't know, a client. I have a directory of salespeople, and I want to know whose client this person is. You know, I'll go all the way down to the end. Who are your clients at the end? I don't know. That's kind of a complicated example. Yeah, going through the maze is a good example. Let's do breadth first, real quick. So this is going to look very similar, but it's going to be similar but different. So the deal with breadth first is that we're going to have people wait in line. People are going to be good about taking their turns. And so you're going to see that D is not going to get buried. So let's start. We'll have our visited. So we're going to start with A, and we say, A, I would like you to get me your get neighbors. I call the get neighbors function. And this time we're going to call it a queue. And a queue is just what British people call a line. So where we say waiting in line, exactly right, Brett. Where we say waiting in line, the British will say queuing. Oh, I'm queuing to see whatever, the Tower of London. The British like to say that they can form a queue with just one person because they're very orderly people and they wait in line. So we're going to start with A. We call get neighbors. And once again, we just have B. And so we put B in line. Mark A is visited. We're going to take B out of the queue. So you start at the back of the queue and you wait until you come to the front of the queue and out you come. So a stack is like a stack of pancakes. You put them on top and then you take them off the top. A queue, you wait in line. So now we say, B, give me your friends. And we have C and D, and they go in queue. And C went in line first. So now we'll mark B as visited. Okay, we visited B. We're not coming back to you again. So C, you got in line first, so you come out of line first. How polite. And once again, I'm going to, because I did this last time, I'm going to make sure we're making connection to F here. Just for the sake of argument. So C, give me your friends, and they can be E and F. They'll go in that order. And we mark C as visited. We're not going to come back to you again, C. We're done. Now D got in line first, so D comes out first. We take D out of the queue. But D did not get buried first. And as a result, we're now visiting all of these friends before we go anywhere else. And so D, we ask, who are your friends? We have F and G, but we're not going to add F twice, so we just have G. And then we're done with D. And so then we would take E out. And E goes there. So let me again pause. And so notice the pattern here, okay? We did all of A's connections. That was easy. Oops. Then we did all of these first friends before we went and did anybody else. And now we're going to do the third layer, E, F, and G. So that's what we call as breadth first. We're going down by layers. We're moving horizontally, if you will, before we go vertically. Let me check Slack real quick. Yeah, DFT is a little confusing to wrap your head around at first. It's probably going to be easier to see with a different graph. This one's a little hard to see it. It helps if you can see us going like all the way down and back up. That makes DFT, depth first traversal, a little clearer. But anyway, let me finish up this. So let's see, we're on E. We could put, E's connection C in into the queue, but so we know we're not going to do anything with that because we've already visited C. And then we're done with E. And so we take F out of Q because that's where F was in the line. And again, we could try to put C in, but we're done with C. So we're done with that. Then we would take G out. G comes out of the queue. And again, we could put, and I forgot to put people in here as I was going. I should put them in as I was going. We could put F in. So then we're done with G's friends. We take C out, but then we're not going to visit C again. So we wouldn't really actually make that the current node. And the same with F. We would be done. We visited everybody. We visited everybody. So here's a good question now. How many times did we visit every node in depth first search? Oops, okay, that's fine. How many times did we visit every node in depth first search? Once. We visited every node once. How many times do we visit every node in breadth first search? Same. Yeah. So, and actually, we also have, notice we're visiting every node once, and we also have to check every connection. We say, hey, for every node, we say, get me your neighbors, right? And then, we'll decide what we have to do from there. So we have to check every node. We have to check every connection. We have to check every edge. So that means that these traversals are linear in the number of nodes plus the number of edges. So you count up how many nodes you have, count up how many total connections you have, and that's how many steps these traversals will take. But they take the same, they have the same complexity. Breadth first and depth first have the same complexity, time complexity, because they are both linear in the number of nodes plus the number of edges. Right. So actually, let me share this screen again. So coming back to this little illustration here. So if we were going through this graph, we would, so this is our little A in the middle, and then we would say, we would get all of the friends. So we're still calling get neighbors, so we get all of them. But now, because they're going to go in a queue, first we visit, say this one, then we visit that one, and so this friend goes in the back of the line, then we visit this friend, and their friend goes in the back of the line, and then we visit this friend, and their friend goes in the back of the line, and so on. And then we come back and we say, you went in line first, we visit you, then we visit you, then we visit you. So with breadth first, we visit all the first order friends, all the friends here, before we visit any of the friends here. And that's breadth first search, breadth first traversal. Well, let's go ahead and code this up. Let me make my font big. Go back to our graph class. How's that? Can y'all see that? Is that good? I'm big in the font. So we're back in our graph class. And, remember just now I said we had a stack, and then I said we had a queue. A stack, you put things, on top and pop them off, and as queue, you wait in line. If we look in the same folder, we have this util file where we define class and stack. And these classes, we have, so a stack we can push onto it, and then we pop off the top. And we can have what size it is. For queue, we say unqueue and dequeue. So you put things in the back of the line and get them from the front of the line. However, if you notice, this is not a real queue. This is a fake queue. The reason being, when we dequeue, what we're really doing is we're using an array here. And then when we dequeue, we're popping off the front. And what's the time complexity of popping off the front of an array? Yeah, it's O of n. So which is so this is really slow. This is a fake queue. A real queue should have O of 1 to pop off the front of it. That's like the whole point of a queue. So this is a fake queue, but we're going to pretend it's a real one when we use it in our graph class, because it's fast for us to do. It's easy for us to do this. So okay, let's come down here. Let's do breadth first traversal. We'll do breadth first traversal. And so the first thing we want to do, why is Q a dictionary? I think, I'm trying to think. That's usually how I've seen a Q represented. So you're right. These curly braces are usually used to mean a dictionary. I'm overloading them. I'm using them to mean a queue, even though that is a different data structure. So maybe in future, I'll just write it like that. Like this is a queue like that. Because this is not a dictionary, this is a queue. Okay, so for our breadth first traversal, are we using a queue or a stack? For breadth first, do we want people to wait in line, or are we letting them pile on top of each other? we're using a queue. We're going to make them wait in line so we visit someone's friends before we visit anyone else. So we make an example of the queue class. And we also want to keep track of people that of those that we visited. And I know I used an array up there, but let's use a set, because set we can check if they're in our set really quickly. So who should go in line first? Who are we going to visit first? We're going to visit, that's right, we're going to visit our starting vertex first. So put them in line. We put them in line, on cue them. So get in line. So they're in line. And how are we going to know when we can stop? How do we know that we visited everybody? Remember, our mission here is to visit everybody. If we visit every node, we win. How do we know when we can stop? Yeah, in this case, when the queue is empty. So, and Andrew's thinking of, he's thinking of iterating through a linked list, which, and actually a queue can be implemented with a linked list. So you're right on with that. But yeah, remember when we say we're going to call get neighbors, we're going to say get your friends, and we're going to put them in line. So as long as there's someone in line, we have someone else to visit. So while q dot size is greater than 0, so while we're not empty, we're going to keep going. And when it's empty, then we know we visited everybody. So while q dot size is greater than 0, we should dequeue the first vertex. We should get the first person out of line. Q dot dequeue. I've just remembered that I should have pseudo-coded this up so that you could see the logic. So let me add some pseudocode. And that way at least you'll have this, and we'll pseudocode up the next one. Nodes, and then we're going to say in line. So while that's not empty, the next node out of line, right? And then what's our, yes, Andrew, probably a linked list would work better than a list for our queue. Probably a doubly linked list is probably the easiest thing to do. At least I always find it easier to work with. You have to be able to pop off the head and add to the tail. So very good. Yeah, super. Yeah, there's also a Python structure called a deck, which has this, it has this implemented for us. Yeah, so we could use a Python data structure called a deck in order to, I think it's like from collections import deck. Anyway, it's a queue basically. So we could use that very easily. And feel free to switch to that. Okay. So okay, we get the next node out of line. What do we want to do now? We have our current node. What do we want to do? Put the current node in the visited, right? Or maybe we want to check if it has been visited. Right? Yeah, which I think is kind of implied by what you said. So if we've not yet visited this current node, actually, let me pseudocode this first, and I'll finish it. If it hasn't been visited, mark as visited, and then what do we do? We'll call yes. We get all of the neighbors. We get its friends. So if it has not been visited, then we'll mark as visited. Get its neighbors. Get all your friends. And then what do we do with each one of those neighbors? Exactly. They can wait in line to get visited. Put them in line to be visited. So let's do that. So if current node not in visited is how we check for membership with a set, just the same way we check for membership with a dictionary. If current node not in visited, then we call visited.add current node. Let me put these in the right place. Mark as visited. And then we will get its neighbors. We can say like edges, you know, it's the same thing, right? Equals, we're going to call self.getNeighbors, right? However we can do that. Get all the neighbors of the current node. And for edge in edges, we then put them in line to be visited. Q.onQ edge. So you can see here, so see here, remember I said this was linear in the number of nodes because we have to touch, so we have to visit every single node, right? We're gonna visit every single node. And then we also have to check every edge. We're gonna, you know, onQ that. Its neighbors, put them in line to be visited. And there we are. We're done. That right there, you know, in these few lines, what is this from, you know, from 39 down to 60s, you know, where we have like 20 lines of code, and half of that is like space and comments. It's like 10 lines of code, and we have breadth first traversal. So with this, we will, I guess this tells us to print each vertex. You know, so really if we want to print, where should we put the print statement? If we want to print this as we go, where should we print? Line 43. Yeah, I might say, we could do that up there. I might say, you know, we want to print every node as we go. So we might do print current node, or we might check we haven't visited it first. So I might say after this, maybe, you know, say, yeah, 56. Yeah. Yeah, so if not, then we say print current node. Okay. Right, we're going a little over time, but don't worry, even though we have all of depth first traversal to do, this is going to be very easy. What's the only difference between breadth first and depth first traversal? Yeah, we use a stack instead of a queue. So copying and pasting is always kind of bad, but I'm going to do it in the interest of time. So I copy all of breadth first traversal. I'm going to scroll down to depth first traversal and paste it in. Boom. So for depth first, so if we use a line, people wait in line. If we use a stack, then as we saw, things get buried. And also if you're like not completely comfortable with this so far, Don't worry, I can do more examples in the instructor hour tomorrow night. So we make a stack, and we put our starting node on top of the stack. And so instead of queued to onqueued, we have stack dot push. We're going to push it onto the stack. Exactly. It's the order we load and unload them. We, oops, put our starting vertex on top of the stack. And the same way, if our stack isn't empty, like a stack of pancakes, then we have more people to visit. So it's going to be the same thing. While stack.size is greater than 0. Then we'll get the next node off the top of our stack. So current node equals stack dot push. No, sorry, not push. We're popping it off. We're taking off the top of our stack. We check if it's been visited. If not, we're going to add it to our visited set. That's still the same. Print it. That's still the same. Get all of its neighbors. That's still the same. And we stack them on the stack to be visited. And as we saw before, that means that anything that was already in the stack is now buried. Push them on top of the stack and bury what's already there. And then we'll go around again. So then we go and get, you know, the next thing that's on top of the stack and pop that off, check if it's visited. If not, mark it as visited, go and call get neighbors and push them on the stack. That's breadth first traversal and depth first traversal. Now, what else is in this file? I'm about to let y'all go because we're a little over time here. One interesting, if we scroll down in this file, the next function is DFT recursive. So one interesting fact is that you can do depth first traversal in a recursive way, but you cannot do breadth first traversal in a recursive way. You can only do depth first traversal in a recursive way, which I always find kind of interesting. So there's a challenge for you. Let me see. So if I go, let me check real quick. I think your project for today is the graph folder. And so you get to rock and roll with doing DFT with recursion and then doing search. Oh yeah, let me cover. Yeah, that's a great question, Jasmine. Is that because recursion is just a stack itself? I think there's some key similarities there. Yeah. So let me, before I let y'all go, I want to do some pseudocode, at least for breadth first search, because that is the next thing you guys get to go off and work on. And I want to talk through the algorithm for that real quick. So the algorithm, the key here is just as before, you're going to make a queue, right? And then we're going to make a set for visited. But the key here is what you on queue. And I will say the first time I did this, I did some weird thing where I backtracked through the I kept track of how I visited them. Then I backtracked, and it was kind of weird. Anyway, it wasn't real efficient. There's an easy way to do this. So in search, we now want to know how we got there. We want to know the shortest path. And it turns out that breadth first search can give us the shortest path very easily. If you're running breadth first traversal, you're also finding the shortest path automatically. And again, I can go over this more tomorrow. With depth first, you're not guaranteed to have the shortest path. You're going to have a path. You're definitely going to get there if you can, but it's not guaranteed to be the shortest. So with breadth first, we can have the shortest. But either way, with both searches, we want to return a path. So here, remember, we unqueued the starting vertex. But here, instead, unqueue a path to the starting vertex. Hence, that's going to be a pretty short path because it's just itself. And from there, it's going to be pretty easy. It's going to be pretty similar, right? We're still going to do while the queue isn't empty, we get the next path. So now all we're putting in is paths. We're not just putting in the vertex. Now the path is going to show, like if I'm going from, if I have, say, A, B, C, and now I'm on C, this is going to show I started A, then I went to B, then I finally arrived here at C. So your current node is the last thing in the path. If I'm on C now, it's the last thing in this path. So you want to get that. You want to get that. And so grab the last vertex off that path, get your current node. And once again, as we did above, check if it's the target. If it's the destination vertex, then what? What do we do if it's the destination vertex? So I said, hey, please get a list showing how we can, please show how we got from A to C. If we're now at C, we say, okay, we're at vertex C. What should I do? In the interest of time, I'll go ahead and answer that. If it is the destination vertex, then we're done. Return the path. Otherwise, if not, mark this as visited, and then just as above, get the neighbors, and for each one, add a path to it to our queue. Okay? So if you do that, and add a path to it to our queue, so you're going to need to, you're going to need to copy the path and then add the neighbor to the path. And then add all that to the queue. So you copy the path, add the neighbor to the copy, and add the neighbor's path to our queue. That's how it's going to work. Append the neighbor to the back.
The path here is the edge.
No, good question. So what we want to do is we're going to return a list containing the shortest path. So the path is going to look like if I went from A to B to C. It's going to look, and so if I wanted to get from A to C, it's going to look like that. So this is going to be your path, essentially. So the path is not the edge, it's how you got there.
Because at first when we are starting, current node is the last thing we are checking. It is the only node, right? There is nothing else there. It is the single node over there.
That's right. Yeah. So the path to it is, pretty short. It's okay. Itself. I mean, yeah. Okay. I am long over time here. My apologies. I'm going to obviously drop this file in Slack. So best of luck with the next challenges. And I hope as you go, you can sort of see the simple logic of, say, breadth first traversal, see how we're building on it. It's going to, because it's going to be, all the other algorithms we learn are just going to keep building on this. And so if you don't get it at first, don't worry. As we go, you'll get plenty of opportunities to practice it and really get that logic down. It's so powerful and fun to work with as you go. All right. Have a good night, everyone.